Okay, so this is Psych 222. It is Friday, February 19th. A reminder that your test one is due at 11 o'clock today, so make sure you submit that. And today what we're going to do is we're going to finish off Chapter 4, the essentials of Chapter 4. So what we were talking about in Chapter 4 before we had the test, we were talking about things like probability. We were talking about the binomial distribution. So remember that last time featured a discussion of the binomial. We computed the probability of 2 heads out of 5 flips of a coin. Okay. And remember, we had to identify things like what is the success and what was the probability of the coin to begin with, which the probability of heads on the coin was equal to 0.5. We assumed that. And all of that allowed us to create the binomial distribution for which we can compute that probability of 2 heads out of 5 flips. Well, you may remember that that distribution, when we were working with that binomial distribution was for a discrete random variable. Okay, so it's for a discrete random variable. So when we look back at that formula for the binomial, all of this, that was for a discrete random variable. And in this particular case, the variable had values of 0 and 1. So it was either one value or another. And that's what made it binomial. On any given trial, the coin could either come up heads or tails. Okay. What's another example of a binomial experiment? Well, in the case of, say, a car crash, maybe you either survive or you perish. That's a binomial situation. What made it a discrete random variable is that we were associating it with a probability distribution. Okay? That's what made it the random variable part. But key here is that it was binomial. There are 2 possibilities for the outcome of the experiment. Now, that contrasts to the situation where almost any value of the variable is possible, not just a 0 or a 1. And that's what we deal with over here. So when we talk about continuous random variables, we're not dealing with that binomial situation. We're dealing with the possibility that any value in the whole interval can happen. And they give some examples here. We'll use our own. Let's say that we take your IQ using an IQ test. Well, the IQ variable is not binomial because you can get almost any IQ in the range of the test. So let's say that the test ranged from 0 to 100, for example. Any value in there is more or less likely in that range of values. That's what makes it a continuous distribution. For instance, you can get 50, you can get 50.1, you can get 50.12. All of those values are theoretically possible. So we have to develop a probability distribution for these continuous random variable types. Why is it a random variable? Well, because we're still going to associate a density distribution with it, but it's not going to be quite the same as in the binomial case. So make sure that when you're looking at this, you have your bearings as to what this heading is about. We dealt with discrete random variable already last time. Now we're dealing with the continuous random variable. And continuous random variables, any values, are possible here in the distribution. Okay. So we say that continuous random variable can assume values associated with infinitely many points in a line interval. And that's exactly what this expresses up here. We say infinitely many because really, if it's truly continuous, any of those values, say from 0 to 100, are possible. There's a whole bunch of values here. That's what defines it as being continuous. So here's a probability distribution for a continuous random variable. Okay. On this axis here is actually going to be something called density. Okay, that's going to be called density. And we're not calling it by the name of probability because notice that we're not having discrete categories of probability. So we're not saying that this is 0.2, this is 0.4, this is 0.6, and this is 0.8, as we would in a probability distribution for a discrete random variable. This is called density over here. It's the height of the curve. Now, the total area under that probability distribution is equal to 1. And that happens to be a pretty much normal distribution here. So that total area is equal to 1. Now, why are we talking about area? Well, we're talking about area, and this is where your calculus knowledge comes in, because we can compute areas under the curve like this using calculus. You may remember integration, right? Integral calculus allows us to compute areas under the curve, and that total area is going to be equal to 1. So if we're dealing with a continuous random variable, we can compute the areas between values on this axis over here. So we can say, well, what's the probability of obtaining a score between A and B? So that's the probability that Y is less than A or less than B, or greater than A rather, because there's a greater sign, or less than B. Okay. That's the nature of the probability distribution for continuous random variables. Notice that up here, we're talking about area. Whereas over here, all of a sudden, we're talking about probability. And that's a little bit of a leap, but it's a convenient leap. If you can define the area under a curve, you can say something about its probability. Now, why does that make sense? Well, here's a very intuitive way of understanding it. If I take what is going to be a square, that's approximately a square, and I divide that square in about 2 pieces, and I ask you to throw a ball at the square, and it has to land somewhere in the square, but otherwise it's completely random. So you take the ball, you throw it at the square. Well, what's the probability it's going to land in this side? What's the probability it's going to land in this side? If it's a completely random process, then that probability is 0.5 and 0.5. There's half and half chance of it lying on either side. And that's because we know it's 0.5 because we can compute those areas in the square, in those different parts. That's the same idea here. If you can compute the area, you can talk about probability. It's a very convenient leap that is made in statistics for talking about probabilities. Okay, so one note here, many people are tempted to say that f of y, like p of y, for the binomial random variable designates the probability associated with the continuous random variable y. Remember, we said that that's not the case. So the book is noting that right here. The authors are telling you it's tempting to associate that with probability. However, as mentioned before, it is impossible to assign a probability to each of the infinitely many possible values of a continuous random variable. So f of y here represents the height of the probability distribution for a given value of y. Now, what does that mean here? Now, this idea here that we have an infinitely many possible values, that means that since there's an infinite number of values, right? Since there's an infinite number of values along that line, so you can even take all of these values here, if you were to try to reach into that line, that one or this one, if you're to try to reach in there and select one of those values, right? You're trying to select one of those values. Well, the probability that you get any particular value, right? The probability of selecting any particular value is equal to, what's it equal to? It's equal to 0. Now, why is the probability of any particular value equal to 0? It's equal to 0 because if there's infinitely many values and it's truly continuous, then you're never going to be able to actually select one particular value. Why? Because those slices get thinner and thinner and thinner. And that's exactly why we need integral calculus to compute those areas under the curve. So that's one important feature of continuous distributions, is that since there's an infinite number of values, the probability of any particular value has a limiting value of 0, right? In the limit, it's equal to 0. So if I were to kind of blow this up a little bit, yes, we can compute the areas between these values and select this value and select this value. But as we get more and more narrow, eventually we cannot get that particular value because it's continuous. And that's why this statement is true. Okay, so here's another distribution here. This one's skewed a little bit. where we may be interested for a score of approximately 80 here. So these are student examination scores. There's a score of 80, goes up to about 100. We may be interested in this distribution. What's the probability of a student scoring higher than 80%? So there's another defined area under the curve that we might be interested in. Again, this is an area, but area is equal to probability. If you can compute the area, you can get the probability. Again, how are you going to get these areas, right? That's what we did when we looked at calculus. That's integral calculus from A to B, or whatever limits of integration you're dealing with. So we'd want to know what's the probability of getting between A and B, between A and B over here, okay? Now, we're not going to do calculus in the course, but it's important that you realize that's where that stuff is coming from, so that when you do see areas under the curve, you have an idea of how that was computed. That's the really important thing here. Okay, so we have different probability distributions, and we're going to talk about these as we go on. We have a normal probability distribution. We have this distribution here called the t distribution, which we're going to develop. That's going to be another probability distribution. We have a chi-square distribution. We have an F distribution. These are all different statistics that are going to be used in our statistical tests. So the book is just showing you a few probability distributions for different statistics. So these aren't real kind of substantive variables. These are just for test statistics of t, chi-square, f, and the normal. We'll talk about those as we go. So here's the first really important probability distribution for continuous random variable, and that is the normal distribution, the normal curve. And so we've been talking about this curve for a while now, and now we're going to talk about how to compute areas under the curve. So if this is a perfect normal distribution, well, we already know that if this value is 0 and you select it at random from the distribution, well, the probability of obtaining a score on this side of the distribution is 0.5. The probability on this side is 0.5. We already know that, similar to the idea that we know that in a square, the probability is 0.5 here and it's 0.5 here. So what we're going to do now is we're going to see how to compute those areas, because usually we're not interested in exactly half of the distribution on either side. We may be interested in what's the probability of getting a score here or greater. So we need to kind of know how to work with that distribution. It goes by different names: the normal curve, normal probability distribution. It's a smooth bell-shaped curve. So remember that when you're dealing with this, that's a normal distribution. I tried to draw one as well as I can. That's a normal distribution. That's a normal distribution. Okay, if I do one down here, that's a normal distribution. It's the general shape of the distribution. This is down here the actual mathematical formula for computing the normal distribution. And notice that in this formula, you have the mean and you have the standard deviation of the distribution. That's what's going to define the given normal distribution. But this is the general formula that's used. Okay. There's more areas under the curve. So we know that within one standard deviation, we've talked about this before, within one standard deviation minus a standard deviation or plus a standard deviation, approximately 0.6826 of the curve lies in that area. Here within 2, we have 0.95. And then if you go all the way to about 3, almost all of the distribution lies within those particular limits. Okay? And again, we know that already. We've talked about this empirical rule of that proportion of cases between values, but what we haven't done is actually know how this is computed, right? We've talked about this number and this number, but we haven't talked about how it's computed. But now we know that if you can compute the area between this value and this value, that area should equal 0.6826. That's what we're talking about now, is how to get those areas under the curve. So talk about area under the normal curve. That's exactly what they're talking about here. Areas under the normal curve allow us to talk about probability. That's really, really important to remember, that we're computing the area not because we want to know the area so much. It's not because in statistics we're really, really concerned with areas. We're concerned with areas at all because we want to talk about the probability. And if you can compute the area, you can talk about probability. Okay, so there's our different areas under the curve. Let's see how all this is computed. Well, we have to define what's known as a z-score. Okay, this is a z-score. Now, a z-score has many uses, but you're going to see that at the back of the book, there's a table, table 1 in the appendix. And that particular table consists of areas under the curve. So remember I mentioned that we can use calculus to get all those areas under the curve, but that's a really, really elaborate process. And oftentimes it's actually quite difficult to compute areas under the curve. Seems like it would be simple, but it's actually relatively complicated. So what we're going to do is we are going to ask the book to compute a whole bunch of areas under the curve for us and to tabulate them in table 1 of the appendix. So what you're going to see in the appendix are those different proportions under the curve. You're going to see them for not only 1 standard deviation away, 2 standard deviations, but a whole bunch of different values along the axis. So that's going to allow us to answer probability problems by using that table. Now, when we start using software very soon, we're going to compute a few things in software, and it's going to report those probability values for us. So we're not going to have to go to a table in a textbook. The software is going to give us those values. But you need to understand what those values are. And those values are going to be those areas under the curve. So this table at the back of the book is called the standard normal distribution. And the standard normal distribution is in units of z. Now, what's a z-score? Well, a z-score is computed by taking the particular value in your data minus the mean of that data divided by the standard deviation of your data. Okay. So for example, let's say that you have a distribution. You can look at the examples here, but let's say the mean of the distribution is 100 and your particular score, okay, your particular score is equal to 10, okay? And the standard deviation is equal to 1. Well, the z-score here is 10 minus 100. Oop, I want to make this 110. Let's make this 110 and this equal to 100. So you are 110 minus 100 all over the standard deviation of 1. Well, that's 10 over 1 is equal to 10. This particular z-score for this observation of 110 is equal to 10. That's what z comes out to be. Now, let's use another example. Let's say that the average on the test, let's do population average, is equal to 80, and that your score is equal to 85. And let's say again that the standard deviation is equal to 1. So you get your test back and we tell you that the average is equal to 80, but your score is equal to 85. Well, what's your z-score? Well, your z-score is 85 minus 80 all over the standard deviation of 1 is 5 over 1 is equal to 5. So you are on the higher side of the curve, and you're actually quite a ways, right? Because you're a z-score of 5. Where's the z-score of 5 here? Well, there's a z-score of 1, 2, 3. Where is 5? 5 is way over here, right? So you did really good relative to the class because your score is way over here. It's way off into the tail. Now, why did you do so much better than the class overall? Well, that's largely due to the standard deviation. Notice the standard deviation is equal to 1 here. What if the standard deviation instead of 1 were equal to 5? If the standard deviation were equal to 5, look what happens. 5 over 5 is no longer equal to 5, is equal to 1. So if the standard deviation were equal to 5, all of a sudden, now you're over here. There's your score. Now you didn't do so much better than everybody else. You're still above on the curve. But because the variability of the distribution has changed, your z-score has changed. And that's really, really important to understand, is that even though your distance from the mean stayed the same, right? That numerator stayed the same, what's going on in the denominator is going to impact your particular z-score. And all we did here was change the value in that denominator. You can make sense of that by thinking about it this way. Now, you got 85, the class mean was 80. Well, if there's very, very low variability, right? If there's low variability, that your score is very extreme. And that makes sense because that means that you scored quite a bit higher than everyone else, because on average, people are not deviating that much. That's what that standard deviation of 1 is communicating. Right now, it becomes really important to understand what the standard deviation is telling us. So it should make sense then that you're getting that z-score of 5, that you're way off into the tail, because there isn't very much variability in the distribution if the standard deviation is equal to 1. But if the standard deviation were equal to 5, all of a sudden that means there's a lot of variability. So your score over here is not as impressive because of all that variability. Okay. So this means as well that we can take a score, subtract the mean and divide it by the standard deviation and obtain that z value, and then refer it to table 1 in the appendix to compute that area under the curve. This is the idea here. We've defined something called the z-score, but we're going to use the z-score to refer it to the back of the book, to that standard normal distribution where we have this distribution plotted at the back of the book. That's going to allow us to compute those areas under the curve. Now, I just want to make a note about this, about how hard it would be if we did not have all those areas plotted at the back of the book. So again, if I just do this for 1 second, mean of 80, your score of 85, and standard deviation equals to 1, well, what do we compute that z-score to be? We said this is 5 over 1 is equal to 5. Well, if I ask the question, how many people would have scored less than 5, right? What's the probability of less than or equal to 5? I would have no way of computing that. I'd have to actually draft the whole distribution with these particular values, and this one too. I'd have to create a whole new distribution to determine that probability. But because we have the distribution at the back of the book, we don't have to do that. We can just refer this information, compute a z-score on it, and get that particular value. So this is the purpose of why we have that distribution at the back of the book, so we can take raw score information and translate it into z-score values. This is what we're doing here. Okay, that's an important point to get as to why we're computing that z-score. It allows us to refer back to that distribution at the back of the book and compute those areas under the curve. And you'll do some examples and assignments of computing z-scores and things like that to get the hang of that and looking at the back of the book. Here's one example where instead of the mean of 100 that we just had, this is a mean of 20, there's a standard deviation of 2. Well, we want to determine the probability that a measurement will be less than 23. Well, there's 23. And when we compute this, we get a z-score of 1.5. Well, just as the book does here, they refer to table 1 in the appendix, and they find that the area to the left of 1.5 is equal to 0.9332. That's all this area over here. So you see, that's why you're using that table at the back of the book. It allows you to compute those areas under the curve. Now, I say it allows you to compute the areas. The areas are already computed, but it allows you to situate those different fractions, proportions under the curve, right? We're not literally computing this area. It's already computed for us, but allows us to find that proportion. Okay, that's the idea. This is a really nice example. Keep that example in mind when you're doing the assignment and you're trying to compute a z-score. This is a good one to refer to in terms of what you're doing. Remember, if the y-score was equal to, say, 20, right? Just for hypothetical, imagine this was equal to 20. Well, what would the numerator be? 20 minus 20 is equal to 0. So whatever that standard deviation is, your numerator is 0. So you're going to get a value of 0. Where does the value of 0 fall in the standard normal distribution? It falls right here. You are right at the center of the distribution. So if you did get a score of 20, well, what's the probability of less than 20? It's 0.5. What's the probability of greater than 20? 0.5. Okay, and again, more examples here, really good examples to kind of get used to that distribution. Here's another example. You can look at more proportions under the curve, and they give a few more over here. Okay, just a quick note, we're not going to spend very much time on this, but this point of random sampling, okay? Whenever you do an experiment, whenever you do a study, it's always a good idea to randomly sample your observations. So if I'm selecting observations from a population, we want to usually, not always, but oftentimes we want to select those observations randomly. And when we think of random selection, we think of this value not having a greater probability of being selected than this value or this value or this value or any other values. Each value should have an equal chance of being selected. That ensures that our statistical tests are valid and accurate. So we need to be able to do that. Now, oftentimes we cannot do that, right? If you think of COVID-19, if you're selecting participants for your study, right? They selected participants to test the vaccine out. Before that vaccine is making its way to us, it had to be evaluated on human beings, right? They did some trials on human beings. Well, they're not going to randomly sample human beings. They can't do that. They have to take human beings who actually want to be in the study, right? So they have to ask people, do you want to be in the study? And if the person says yes, well, then they could be in the study. They can't simply go out into the population, you know, start flipping coins, some random process, and select people and say you're going to be in the study. So random sampling, when you really start doing research, is actually quite hard to do with human subjects. If you don't randomly sample, you may come across a selection bias. And that could happen if you are selecting people of certain ages, or you have any other kind of bias when you're doing the sampling. Now, in psychology experiments, oftentimes we are selecting a volunteer, just like in the COVID-19 study. Well, there's sometimes documented this idea of volunteer bias. Right? So if you can only select people who volunteer for the study, well, maybe those people aren't always the same as people who wouldn't volunteer. Right? So for instance, let's say we were doing a study and we wanted to evaluate how good of drivers people are. Right? We want to evaluate driving behavior. Right? Driving behavior. Well, if I went into a group of people and I asked who wants to be in the study, right? I needed, say, 10 people to be in the study. Well, maybe the people volunteering are actually people who are good drivers because they like to show that they're a good driver, right? So if I ask who wants to be in the study for driving, there could be a selection bias there because maybe I'll just get good drivers. The people who are bad drivers, maybe they don't want to be in the study because they know they're not good drivers, so they don't volunteer. That'd be an example of a selection bias, and that can happen. Okay, there's the idea of the random sample. So equal chance of being selected. There has to be an equal probability of being selected. Here's an example here, not necessary to review, but you can if you want a little bit more information on the ideas of picking a random sample. These are random number tables, can be constructed as one way of getting a random sample. And you can read there on how they work, but it's not crucial information because most of the time when you select a random sample, you're going to allow a computer to generate pseudo-random numbers for you. And remember that when you're dealing with a computer, you're not really dealing with random numbers. You're dealing with what are often called pseudo-random. So even when we ask the computer, select a number between 1 to 10, That's not a random process really, but it's close enough to it that we can think of it as being random. Now, why isn't it random? Because whenever you ask a computer, which is based on an algorithm, to select a random number, it's doing it based on some formulation. So it cannot really be random, but it's close enough. We call it pseudo-random. Okay, and again, you don't have to look at that very much. That's understanding random sampling is enough. You don't have to go into detail in terms of using that random number generator. This is really, really important. Okay, so sampling distributions, very, very key concept in terms of understanding where we're going and understanding statistics in general. Well, I'm going to put an example here, and I'm going to say that we have a distribution over here, and that distribution is a distribution of IQs, and it has a mean of 100. So there's my distribution of IQs. Now along here are a whole bunch of IQ scores. So let's imagine that this is the IQ distribution of the USA. And we have the mean is equal to 100, but this particular value here is a score. So that's an X sub I score. There's another value of IQ over here. So we have a population of IQ scores. Well, what we're going to do is we are going to be using means a lot when we run our studies. When we look at different studies, we're going to be computing things like means. So if you want to study means, then you have to derive a distribution of means. Okay. So let's say that I went out into Montana. Okay. I went out into Montana and I wanted to look at the distribution of scores in Montana. I want to know what the IQ was of Montanans on average. Okay. This is for the whole population of the USA, but I want to know on average, how do Montanans score on IQ? So let's say that the mean I get for Montanans is equal to 115. Well, I cannot compare this average IQ directly to this distribution because this is a population distribution, but this is a mean over here. So I cannot go into this distribution and put 115 somewhere over here. I can't do that. Now, why would I want to do that in the first place? I'd want to do that because I'd want to know where does 115 fall in the IQ distribution, right? Is this far away from the mean? Is it close to the mean, right? What's the probability of getting a score like this if it was really drawn from this population distribution? Okay, and that's an important question because does this indicate that Montanans are very intelligent, or does it still indicate that they're close enough to being about average? But the problem again is I cannot compare an average directly to that distribution because that's a distribution of scores, but this is a mean. So what we need to do is we need to derive what's called a sampling distribution of the mean. We need to derive a sampling distribution of the mean. What's the sampling distribution of the mean? More generally, it's the sampling distribution of a given statistic. In our particular case, we want the sampling distribution of the mean. What the sampling distribution of the mean here is the distribution of a statistic for all possible values of that statistic. So what does that mean? That means that I want a distribution that represents if I went into this population repeatedly, right? If I went into this population repeatedly and collected sample means, what kind of distribution would I get? So that is what's going to be called the sampling distribution of the mean. Well, the sampling distribution of the mean is going to have a mean equal to 100. So if I continuously sampled from this population distribution, the average of all of those means I could collect is going to be equal to 100. It's going to be equal to the average of the population. And that might make some intuitive sense when you think about it, why that should be true, right? If I went into a population and started collecting means and plotted all those means, well, it makes sense that the average of all of those means should equal to the same mean of that population. That's why I'm putting 100 here. But what we don't know are the standard deviation bars of that distribution. So again, this is the sampling distribution of the mean, but I don't know what these standard deviation bars are, the values of them. So this is 1 standard deviation away, this is 2, and this is 3, but what value do I put here? Is this 101? Is this 102? I just don't know. So we need the standard deviation of this sampling distribution. That standard deviation of the sampling distribution, okay, we talked about the standard deviation of the sampling distribution, is what's going to be called the standard error of the distribution. Okay, it's going to be called the standard error of that distribution of the mean. So here in the book, they summarize the idea that we just talked about. The average of all of those sample means is equal to the original population mean. That's why we put this at 100. And this at 100. 100, the average of all the means is equal to the mean. But this is what we were trying to compute just now. We were trying to conceptualize what's the standard deviation of all those means. That standard deviation is called the standard error of the mean. And this is how it's going to be computed. You take the population standard deviation and you divide it by the square root of n. Now, what's n? Size of the sample. Okay, this is the size of the sample on which you're computing all of those mean values. Okay, this is really important to understand what this n actually is. It's the size of the sample on which you're computing mean values. It's not the number of samples you're taking. Okay, this is not the number of samples you're taking, because if we're producing the sampling distribution of the mean, well, in theory at least, we're taking an infinite number of samples. On each sample, we are gathering a certain number of observations. So let's say we're gathering 10 on sample number 1. Then we're gathering 10 on sample number 2. Then 10 on sample number 3, and so on. We're getting an infinite number of samples, so we're going to infinity with the number of samples, but on each sample, we're collecting a sample size of 10. That's what the n represents, is this number right here. It does not represent an infinite number here, because otherwise we would not be able to compute that. Okay, so again, this is going to be called the standard error of the mean, and the standard error of the mean is the standard deviation of all of those mean values. Okay, really key concept to understand what that is. Well, we need to talk briefly about a theorem here, and that's called the central limit theorem. So we said that if you continuously sample means from that population, we now know that the mean of all of those means is going to be equal to the mean, right? The mean of the population from which we're sampling. 1 standard deviation bar is equal to the standard error, right? There's 1, there's 2, and there's a third standard deviation away from the mean. Well, we'd like some assurance that that distribution, right, this sampling distribution, we'd like some assurance that this sampling distribution is going to be normal in shape. We'd like some assurance of that. Now, why would we want to know that? Well, we want to know that because that table 1 at the back of the book, right, in the appendix, that distribution has a normal shape. So the distribution that we're working with, we want to make sure it looks like this. And it makes sense, right? Because we're going to be computing probabilities in this distribution. And then we're going to be referring to the table to determine, you know, those areas under the curve. Well, it makes sense that we should require this distribution to be normal if we're going to be comparing it to a normal distribution at the back of the book. And up to now, we haven't said how we're going to know it's normal, but this is where we're at right here. The central limit theorem tells us that this sampling distribution is going to be normal in shape. Okay. And here's some examples here of what happens as you have bigger and bigger sample sizes here. So here's a sample size of 5. Notice that the distribution is not very normal. It's not too bad. But as you increase the number, the distribution more and more starts to resemble normality. And that means that in our formula here, as n goes up, right, as n increases, well, the distribution is more likely to start being normal in shape. For small n, we just don't know what it's going to look like. But for larger n, we can say that the distribution is going to start to resemble normality. So let me just clean this up here a little bit, make it a little bit more clear. There's our standard error. As n increases, we eventually get a more and more normal shape. That's what this idea is communicating, but they're doing it for the median instead of the mean. But the same idea is there. Okay, so there's our central limit theorem for the mean right here. Well, it summarizes all the information that we've just talked about. So this is a really nice summary here of the last like 4 or 5 pages of what you need to know. The average of all of those sample means is equal to the mean. The standard deviation of all those means is equal to the standard error. When n is large, the sampling distribution of the mean will be approximately normal, with the approximation becoming more precise as n increases. That's exactly what we just said. As n increases, you get closer and closer to that normal distribution. When the population distribution is normal, the sampling distribution of y is exactly normal for any sample size n. Now, what does that mean? We haven't talked about this one yet. That means that if you're sampling from a population distribution that is perfectly normal, then your sampling distribution of the mean is going to already be normal, regardless of the size of the sample size. Regardless of that sample size, you're already going to get the normality. But if you're sampling from a population, let's give a different population that looks like this, I mean, that's not normal. As n increases, you're still going to get a pretty good approximation to the normal distribution. That's what this is saying right here. So even if you're sampling from non-normal populations, the approximation becomes more precise as n increases. But if you do know that the population distribution is normal, then you already have the normality. So we see where the central limit theorem is important. It's mostly important when we don't know what that population distribution looks like. That's where we really want to rely on the central limit theorem. Now, maybe we don't know what the distribution of IQs looks like. Right? Maybe the distribution is actually skewed. Maybe it's like that, right? The USA IQs are like this. We don't know. Well, when you create your sampling distribution of the mean, you have to make sure that your sample size is sufficiently high to ensure the normality of the sampling distribution. That's the idea there. Here's some distributions, some sampling distributions for different sample sizes. So even when you have a population of a given shape, we know normality is going to hold thanks to the central limit theorem. That's what the central limit theorem is communicating. So it's a really good theorem that we have at our disposal. Otherwise, we wouldn't know what that distribution is supposed to look like. Okay, there's some other central limit theorem for the sum of y, different sampling distributions. We're going to be working with the sampling distribution of the mean. We've talked about what that sampling distribution is. They talk about different interpretations here. You can read that over. And this is definitely where we're going to stop. Okay, so up to here, and that's it for the chapter. So and I will recap these ideas next time because there's a lot of ideas and as we close out this chapter, and this chapter has been pretty big in terms of ideas overall. But just to close out the idea of what we're talking about here, always go back to that example that we're talking about with the IQs. You know, remember, what did we do? There's our population mean. Here are all the values of IQs. Well, I want to derive the distribution of means from here for a given sample size. So if I derive the sampling distribution, what's the distribution of means look like? Well, we said that the average of all of the means you can collect is equal to the population mean with standard deviation equal to sigma over square root of n. This normality that I just drew in, right? How did I know it was going to be normal? Right? How did I know this distribution of means was going to be normal? How did I know? By the central limit theorem. That's what we just looked at. Okay? That's about the last 40 minutes of what we've been talking about is all summarized here. And we're going to see how this is used in evaluating hypotheses starting next week. But that's what the big idea is here. Now, let's just recap the other idea we talked about. We talked about z-scores. Well, y minus the mean all over standard deviation. When you compute a z-score, it computes it, it translates your information into units of the standard normal distribution at the back of the book. And that standard normal distribution at the back of the book is a z distribution, and it is perfectly normal. So starting next week, we're going to be using this information to address hypotheses. And so we're going to see it over and over again. But these are the central ideas here. So we're all set now to start computing some statistics next week, and we're going to see how this stuff is used. So if this is taking a little bit to absorb and you're not quite sure of, what is the sampling distribution about and what's going on here, it's going to start to make more sense next week when we start applying it to problems and we see these features come into play. Okay, so that's it for this week, and we will see you next week.